My today's topic is cumulative distribution function or simple distribution function, simply distribution function corresponding to discrete random variable. Okay, I have not yet uh, entered into the domain of continuous case because we still are studying the module 1. In module 1 there is no continuous case, all cases are discrete. And here you see that I have written the definitions which I discussed in my last class once again. The definition of distribution function, this definition, and the properties of the distribution function. These are the two properties. Now the definition of distribution function has already been applied in one of the examples. Now I'm pretty sure that if you are missing something, that means one example will not be sufficient to clarify your doubts about distribution function. Okay, because of this symbol less than or equal to, whenever there is less than or equal to, always think that we are prejudiced. We think that less than or equal to means something which is continuous. It is not like that. Less than or equal to means capital X can take the discrete values also. So I have decided to show you one more example corresponding to this particular definition, and then I am going to discuss today the theorem which I stated in the last class, but no problems have been discussed. The theorem is this. Now I am not going to read the theorem right now. I am going to show you in front of the screen. I'm going to show you this once again once I start discussing the appropriate example. But for the time being, you don't have to write anything. You just see what I'm saying. I'm going to discuss a problem first of all, which is based upon the definition of distribution function for discrete random variable. Another problem. What is the problem? I'm not considering any tough problem. I'm considering an easy problem over here. The problem is this. You can write down the question in your copy quickly. The problem is 2 socks are selected at random and removed in succession from a drawer containing 5 brown socks and 3 green socks. Okay. List the elements of the sample space and the corresponding probabilities. Define the random variable that denote the total number of brown socks selected. Find the distribution function of the random variable and plot its graph. Okay, since I'm going to scroll down now, you quickly note down this question. Okay, just important parts. Here 2 socks are there. Out of them 5 are brown socks, 3 are green socks. Okay, they are selected at random and removed in succession. We are going to list the elements of the sample space and the corresponding probabilities, and then we are going to define a random variable which is actually the total number of brown socks selected out of all the outcomes of the sample space. And then lastly, the distribution function of the random variable, and we are going to plot this graph. Now I shall be doing the solution. I will be writing the solution of question A and question B together. Okay, in one chart. So that's why I have written here A and B. Now what is the solution? 2 socks have been selected at random and they have been removed in succession. They have been removed. That means the socks have been selected without replacement. If this line is not there, the calculation will change. Removed in succession means once you select a sock, you keep it aside, you are not putting it back, and then you are selecting the next one. Okay, so that is a particular kind of selection which is known as without replacement. So with respect to this, what do I get? Let me see. This is my chart. This first part is called the element of sample space. Okay, the first part is called the element of sample space. Second part gives you the probabilities of the outcome, and third column gives you the random variable, which is nothing but the total number of brown socks as defined in the question. Now let us denote the random variable by capital W. and small w is one of the values of the capital W. Okay. Now, what are the possibilities? Since two socks are selected at random, the possibilities are this. BB means both the socks are brown. BG means first sock is brown and the second one is green. GB means that the first one is green, the second one is brown, and the last one is GG, means green. Now, how many brown socks are there? 5 brown socks are there. 5 brown socks are there. Let me see what is given in the question once again. 5 brown socks and 3 green socks are there. Okay, so with respect to this information, I am going to calculate the probabilities. Since it is without replacement, I calculate the probability in this way. Total case will be 8C1 into 7C1. First, we are going to select one item out of 8 items, so in 8C1 ways. And since it is replaced, it is removed, then the second item is selected from 7 items, remaining 7 items. So we get 8C1 into 7C1. And similarly, there were 5 brown socks. So first brown sock can be selected in 5C1 ways. The second one can be selected in 4C1 ways because the first one has been replaced, has been removed. So that's how we calculate the probability 5 by 14. Okay, probably you have understood. Second one talks about BG. So in all these probabilities, the denominator will remain same. It will be 8C1 into 7C1. Numerators will keep on changing. Since I'm talking about BG, so the brown sock, one brown sock can be selected from 5 brown socks in 5C1 ways. And one green sock can be selected out of 3 green socks in 3C1 ways. So we calculate the probability that is 15 by 56. GB, similarly we get 3C1 into 5C1 by 8C1 into 7C1. And GG is, first of all, we are going to select one green sock from out of 3 socks and in 3C1 ways. And then since one sock is replaced, then another green sock can be selected out of the remaining green sock, that is 2, in 2C1 ways. So we get 3C1 into 2C1 by 8C1 into 7C1. So we get 4 probabilities, 5 by 14, 15 by 56, 15 by 56, and 3 by 28. Capital W is the random variable which denotes the total number of brown socks selected in each of the outcomes. Okay, so what are the values of the random variable? If we see the first outcome, total number of brown sock will be 2. If we see the second outcome, the total number of brown sock will be 1. If we select the third outcome, the total number of brown sock will be 1. And if we select the last outcome, the total number of brown socks will be 0. So the random variable has got the values 0, 1, 2. And you know this is a subset of set of real numbers. Again, defining that a random variable is a function from sample space to the subset of set of real numbers. Our next job was to, what are the probabilities of this random? If I talk about the random variables, what are the corresponding probabilities? Okay, so let us calculate this. So I have prepared another chart where I have considered the random variables only. Okay, not the individual probabilities. So the first column is capital W equals to small w. These are the 3 possible values of small w, 2, 1, 0. They are distinct values. Okay, and small pw is the notation, which means the probability that capital W takes the value small w. Now, from our previous chart, we are just putting the values over here. When the probability that W equals to 2, there was only one case and the probability was 5 by 14. So I have written here 5 by 14. But W equals to 1 can happen in 2 ways, either BG or GB. So the 2 probabilities will be separated and we'll take their summation individually. So we will take the sum of 15 by 56 and 15 by 56 twice. So we get twice 15 by 56, that is 15 by 28. And W equal to 0 can occur only once with respect to GG, and the probability is 3 by 20. That is how we have tabulated all the probabilities over here. Now our job is to find the distribution function. Just like we did in the previous example. The distribution function's definition I have mentioned. Just to clarify what I am going to do over here. This is the definition of distribution function. I am going to calculate the values individually. First of all, I am going to calculate the value where W takes the value 0, then W takes the value 1, then W takes the value 2. F0 becomes probability of X less than or equal to 0, which is summation small t less than or equal to 0 Pt, and that is P0. This particular calculation has already been explained to you in the last class. So we get 3 by 28. F equals to 1 means probability of X less than or equal to 1, summation over t less than or equal to 1 Pt. So we get P0 plus P1, and we add the two probabilities, we get 9 by 14. And F2 can be similarly calculated as 3 by 28 plus 15 by 28 plus 5 by 14. And the total probability is 1. And this implies that our calculation of distribution function is correct, because we know that total probability of the probability mass function must be same as the last value of the distribution function. And you know the probability mass function summation give you 1, so F2 must be equal to 1. So this is my values of these are my values of the distribution functions. What is my distribution function? We have to write this distribution function in its function form. So I have written this as below, which is given as Fw. When small w is less than 0, the value is 0. When w lies between 0 and 1, then it is 3 by 28. When it lies between 1 and 0, then it becomes 9 by 14. And when it becomes w greater than or equal to 2, then it becomes 1. So I have tabulated all, I have taken all the values from my calculation, and I have serially organized them with respect to the defined range. So if we keep the distribution function in this way, nobody will say this is a distribution function. Everybody will say these are the values of the distribution function. You have to summarize all the values together properly, showing the range of the random variables. Okay. Now the thing is that why this problem is important, it's just because why I actually redefined it is because of this notation. Whenever we apply inequalities, when we write that X lies between something and something, then automatically we are prejudiced that something, maybe we are talking about continuous case. But no, lesser than inequality has nothing to do with continuity. Lesser than inequality may be there, but here lesser than inequality means the value is taking, the value which lies between the upper and lower limit takes the discrete values. In continuous case, the only difference is that the values take the continuous, it ranges in continuous spectrum. But here the values may lie between two. If I say talk about natural numbers, and if I say small x is a natural number which lies between 1 and 10, 1 including, 10 excluding, you will not say x takes every possible value between 1 and 10. You will say, yeah, okay, fine, x is equal to 1, 2, 3, 4 up to 9, but x cannot be 10. That's what I'm actually trying to say. And once we get the function, the graph is plotted in this particular manner. So you see, when x less than 0, when w is less than 0, so there is nothing shown in the graph. Okay, no value. When w equals to 0, lies between 0 and 1, so means w equals to 0, so the value is 3 by 28, and it keeps on taking the value, this particular value, it remains fixed until and unless it reaches 1. Once it reaches 1, it jumps to 9 by 14, it takes the value 9 by 14. And it keeps on taking the value 9 by 14 until and unless it reaches the value 2. And once it gets the value 2, it jumps to 1. And it keeps on going like this, 1, 1, 1, 1, 1. Any value greater than 2, the probability, the distribution function gives that the probability is 1. Okay, so actually the distribution function always gives you a step function. Distribution function is always giving you the step function. Now, this problem is done. What is my next problem? My next problem is a bit important problem. What is that? If capital X is the distribution function. Now, in the previous case, we calculated the probability mass function, and out of that we calculated distribution function. Now here the thing has been reversed. Distribution function is given. We are going to find the probability mass function. How to do this calculation? The reverse calculation. And once you if you can calculate the probability mass function, each of these values can be calculated. So with respect to the information given, you just quickly note it down in your copy. You note down the function given over here. If this function is there, then I'm supposed to find the probability that capital X lies between 2 and 6. I'm supposed to calculate that capital X lies between capital X takes values 4, and the probability distribution. Okay, what I will do is that I will first calculate the probability distribution, and then I will calculate these two products, these two probabilities. Okay, so first of all, I'm going to show you how to find probability distribution if distribution function is given. Here I'm going to apply this result, this theorem. What is the theorem? If the range of the random variable capital X consists of values x1 less than x2 less than x3 less than ... less than xn, then f of x1, the probability of that the random variable takes the value small x1, is the distribution function's value at x1, and the probability that the random variable takes the value xi is the difference of the distribution function's value at xi and distribution function's value at xi minus 1. Here I will take the values from 2, 3 to up to small n. This is very important theorem, and if you can recall, and if you cannot recall, you see my earlier video that I told you that I'm going to show you how to apply this theorem to the problems. Now is the time to show you how to do this. So let us go back to our problem, the question number 2. And in question number 2, I have again mentioned the theorem once more, so that it always remains in front of you. I have restated the theorem, okay, which was written in page 1, so that it always remains in front of your eyes. So I am going to show you how to apply the theorem for the given problem. Okay, so I hope you have noted down the theorem. Quickly you note down the theorem and the function. I am going to tell you how to do the calculation. Okay, so okay, I'm saving your chat to be on safe side. Meanwhile, probably you have all written down the function. Quickly you write down the function and the theorem. The theorem has been taken from the John Foynt book of probability and statistics, which I shared with you in Google Classroom. Okay, I'm scrolling down, and if you miss anything, then no problem. I'm again going to show you, and you are going to get in the note. The video of this class will be uploaded tomorrow, not today. Okay, it's because this class has not yet been taken for ECB, and if I upload the video today, then maybe ECB students may not join my class tomorrow. Okay, so that's why once a particular topic is finished for both the class, then I upload the video. This is what I do actually. Okay, otherwise if they see the video, I have to prepare again another note, and that will be very hectic. So actually, since there are 120 students and I'm going to teach all the students the same thing, why to do the extra job? Okay, one note, two batch. Now, since it is given, since this condition is given in the problem, you see carefully, you see that capital X consists of the values small x1 less than x2 less than x3 less than xn, I'm going to formulate a table in the following manner. What is the table? I'm going to name the values. How do I get the values? You see, from the question I'm getting the values. In question, the value is starting from 0. I'm taking it from 0 and it goes up to 10. Okay, so that's why I'm naming all the items from x1 to x10 with respect to the values given. So I'm writing here, I'm naming x0 as x1, 1 as x2, 2 as x3, 3 as x4, 4 as x5, 5 as x6, 6 as x7, 7 as x8, 8 as x9, 9 as x10, and 10 as x11. Now you may ask me whether it is important or not. No, this step is not important. But from pedagogical point of view, I'm just showing you the chart so that it always it should help you in understanding what I'm going to do with the calculation. You can, if you are well versed with the problem, then you can easily skip this particular chart. No problem with that. Now once I do this, I'm going to calculate all the probabilities individually. So px1, what is the probability? What is x1? X1 is 0. And what is p0? P0 is f0. Why? See, why is it so? fx1 is equal to fx1. The first value, the probability at the first value is same as distribution function at the first value. Distribution function's value at the first value. So therefore, my first value is 0 according to my chart. So px1 is p0, which is equal to f0, which is 0. px2 is p1. Now try to recall what was pxi, fxi, small fxi. It was capital F of xi minus capital F of xi minus 1. Now in place of small f, I'm writing small p because I'm dealing with probability mass functions. Okay, notations are not important over here. If you know the meaning of the notation, that is all right. So p1, so by the definition, it should be f1 minus f0. And what is f1? F1 is 1/3. You see, what is f1? F1 is 1/3. And what is f0? F0 is 0, so it is 1/3. px3 is p2, which is f2 minus f1. What is f2? See the chart. 2 is a number lying between 1 and 4. So f2 is also 1/3. And what is p1? Sorry, f1, you have already calculated, that is 1/3. So 1/3 minus 1/3, that is 0. px4, p3, f3 minus f2. What is f3? See from the chart. f3 is 1/3 because it lies between 1 and 4. So it becomes 1/3 minus 1/3, that is 0. Similarly, px5 will be p4, which is f4 minus f3, which is half minus 1/3, that is equal to 1/6. Why f4 is half? See the chart. When x takes the value 4 to 6, the value is half. Remember this, or if you have written already, then it is in front of you. Just check. So it becomes half minus 1/3, it is 1/6. px6, which is p5, f5 minus f4, which is half minus half, that is 0. px7 is calculated as 1/3. px8 is calculated as 0. px9 is calculated as 0. And px10 is 0. And lastly, px11 is 1/6. So some probabilities are 0 and some probabilities are non-zero. I have tabulated all the probabilities here. Okay, p0 is 0, p1 is 1/3, p2 is 0, p3 is 0, p4 is 1/6, p5 is 0, p6 is 0, p7 is 0, p6 is 1/3, p7 is 0, p8 is 0, p9 is 0, and p10 is 1/6. Okay, so I have tabulated all the values of the probabilities. Okay, probability mass function. And you see, what do I get? The above is a probability mass function. Why is it probability mass function? Because its sum total is 1. You take the sum total of these non-zero probabilities, the sum total is always gives you 1. Now here is a question to you. You can think and write the probability mass function. The values here, the values have been given over here, but you can write it in a functional form. I have not shown it here. You try to do it by yourself. Try to think what functional form can be put with respect to this chart. Okay, try to think. Okay, it's a question for you. And once this chart is in front of you, probability of x equal to 4 can easily be calculated, which is P4, and P4 is 1 by 6, directly from the chart. And if x lies between 2 and 6, then means capital X is discrete, so it takes the value from 3, 4, and 5, and 6. 2 is excluded. You have to be very careful where the equality sign is. So if we write 2 less than or equal to x, then probability will change. Now, if we include 2, here for this particular problem, the probability will not change because P2 is 0. But you have to be very careful which one is excluded and which one is included. So we write all the probabilities over here and we calculate this. P3 is 0, P4 is 1 by 6, P5 is 0, and P6 is 1/3, and we get half. So the problem is done. That's how we find the probability mass function when distribution function is given. One practice problem I have introduced over here. The practice problem is, you are going to find, and it is very easy, you are going to find the expectation and variance of the random variable capital X for question number 2. So use the formula of expectation and variance and find these values. Okay, and see what comes out. Before I conclude my today's class, I am going to show you some important results. Okay, the proofs are not there, you just remember, and whenever necessary we shall be applying this. What are these results? The results are, if we talk about two random variables, and if these random variables capital X and capital Y are independent random variables, then this is satisfied. What is the formula? Formula is expectation of capital XY, capital X into capital Y. Capital X into capital Y means here multiplication sign is not there. It is not X into Y. It is X intersection Y. We take the intersection part of the two events. Okay, the random variables. So expectation of X intersection Y will be the product of their individual expectation. And variance of X plus Y will be variance of X plus variance of Y, if the variables are independent. But if the variables are not independent, then E of xy is not equal to Ex Ey. Okay, and variance of X plus Y is Vx plus Vy plus 2. This term is called covariance xy. When we'll be studying correlation, we'll be knowing what covariance is. For the time being, I'm skipping it. Okay, so covariance xy. Variance of x plus y is variance of x plus variance of y plus 2 covariance xy. And variance of x minus y will be variance of x plus variance of y minus 2 covariance xy. So therefore, I have written here variance of x plus minus y as variance of x plus variance of y plus minus 2 covariance xy. Now, covariance between two random variables is actually denoted in terms is denoted by cov xy and is defined in terms of expectation as this. It is expectation of x intersection y minus Ex Ey. Now you see, if I ask you, if capital X and capital Y are independent random variables, what will be covariance? You know that for independent random variables, these two items are same. So in that case, covariance of xy will be this minus this, that is 0. Covariance xy in that case will be 0. And since for independent variables covariance of xy is 0, you put the value over here. What do we get? Variance of x plus minus y becomes Vx plus Vy. So from here we get another result. So for independent random variables, not only V of x plus y equal to Vx plus Vy, V of x minus y is also Vx plus Vy. Plus minus sign comes over here, not here. Remember, very important result. These three results are interrelated to one another, interconnected to one another. And for any two random variables, x and y, not necessarily independent, E of x plus minus y is ex plus minus ey. Okay, if it is ex plus y, that we get ex plus ey. If it is ex minus y, then we get ex minus ey. And for any random variable capital X and for any constant small c, these are the properties. Expectation of c into x is c into expectation of x. Constant is not affected by the expectation. Variance of cx is constant comes outside the variance sign, but then it gets squared. So v of c into capital X gives you c squared vx. Expectation of constant is constant, has already been explained to you in my earlier class, and variance of constant is 0 because for constant there is no variation at all. So students, I am going to finish my today's class at this point. This is my today's class. These are my today's topic. Tomorrow I am going to start my module 2. Okay, but you don't have to think much about module 2. You just keep on thinking about keep doing sums related to module 1, because your examination is coming, quiz test is coming. So concentrate on module 1. Okay, for the time being, don't think much about module 2, but you attend the class, you try to understand what I say, and I hope that all of you are going to get good scores in the examination. So for today, with this I'm going to conclude my today's class. Hope you have understood, and I'm going to upload the video tomorrow. I'm going to upload the note tomorrow in the Google Classroom. Okay, so bye for now, and stay healthy, stay safe.